Welcome to The Explainer. Today, we're diving into something really cool: how to predict the future using one of machine learning's most powerful, fundamental tools. We're going to take simple data and turn it into a real forecasting engine, all with just a few lines of Python. I know it sounds a little bit like science fiction, right? A straight line predicting the future? But in the world of data, the answer is a definite yes. The key isn't just any line. It's finding the one single right line. Let's see how it's done. So let's meet Jeff. He runs an ice cream truck, and he's got a classic business problem. He knows that when it's hot, he sells more ice cream. Duh, right? But every single morning, he's just taking a wild guess at how much to make. And that guesswork is costing him. Some days he runs out and loses sales. Other days he makes way too much and it all melts. What if he could stop guessing? So here's the plan. We're going to follow Jeff's journey from start to finish, using a real-world professional data science workflow to crack this problem for him. Okay, first things first. Just like any project, before we start building, we have to get our workshop in order. For us, that means loading up the right software and getting all of our data formatted in a way the computer can actually understand. It all starts with these two lines of code. The first one imports NumPy, which is the absolute foundation for doing any kind of serious number crunching in Python. The second line pulls in the linear regression model itself from a library called Scikit-learn, which is the go-to tool for machine learning pros. Next up, we need to take Jeff's messy sales log and give it some structure. We'll use those NumPy arrays we just imported. Now, in the data science world, we have a little convention. We call our input data, the thing we know, like temperature, X. And we call our target, the thing we want to predict, like ice cream sales, Y. Okay, now for the really cool part. This is the learning in machine learning. We're about to feed Jeff's historical data to our model and literally ask it to find the hidden pattern connecting the temperature to his sales. So what's actually happening under the hood? What's the goal? Well, the model looks at all those individual data points from Jeff's log, and its entire job is to draw one single straight line right through the middle of them. Not just any line, though. It has to find the one best fit line that gets as close as possible to all the points at once. But best is a fuzzy word, right? How does a computer define best? It uses something called mean squared error. Here's how it works. It measures the distance from every single data point to the line, squares that number, and then calculates the average of all of them. The model's goal is simple: find the line that makes that final error number as tiny as possible. And how does it find that lowest point? Well, that's where this awesome algorithm called gradient descent comes in. The best way to think about it is like this. Imagine a giant valley where the lowest point represents the lowest possible error. Gradient descent is like putting a ball at the top of that valley and letting it roll. It will naturally find its way to the very bottom, and not bottom point gives us the perfect line. And get this, all of that complex math, the ball rolling down the hill, finding the minimum error, it boils down to just two lines of code. Seriously, first we create a fresh, empty model. Then we use the .fit command. That's it. That's the go button that tells the computer, hey, do all that hard work and find me the best line for this data. Okay, the computer did its thing. It found a line. But are we done? Nope, not even close. As a good data scientist, you never just trust the machine blindly. We have to check its homework and make sure the model is actually any good. So, how do we grade it? We use a score called R-squared. Think of it like a report card for your model, on a scale from 0 to 1. It basically tells us what percentage of the change in ice cream sales can be explained by the temperature. A score close to 1 is an A+. A score near 0 means the model is useless. So we run the code, and boom, 0.98. Wow, that's basically an A+ in the machine learning world. A score that high tells us that our simple, straight-line model has done an incredible job of capturing the pattern in Jeff's sales data. We can definitely trust this. All right, this is it, the moment of truth. We've got a trained model, we've checked its work, and it passed with flying colors. Now, let's actually use it to solve Jeff's original problem and figure out how much ice cream to stock. So what did the model actually learn? Well, it learned a simple equation, the exact formula for that best fit line. And that formula is defined by just two numbers, the slope, which is the steepness of the line, and the intercept, which is just the starting point. And the cool thing is, we can actually peek inside the model's brain and see these two numbers it calculated. the slope, is super useful. It tells us, for every single degree the temperature goes up, exactly how many more ice creams Jeff can expect to sell. The intercept is kind of like our baseline, the theoretical sales on a freezing 0-degree day. So let's do it. Let's put this thing to work. The weather forecast says it's going to be a scorcher tomorrow, 35 degrees. This is a temperature the model has never seen before. We just feed that new number into its .predict function and see what it says. And out pops a number, 325. There it is. Jeff now has a real data-driven forecast. No more guessing, no more wasted money or lost sales. He knows exactly how much stock to prepare. Okay, so Jeff's problem was kind of perfect, right? The data was clean, everything worked smoothly, but in the real world, you are absolutely going to hit some snags. So let's talk about the number one error that trips up almost every single beginner. You'll see this error a lot. Scikit-learn is, let's say, picky about the shape of your data. It expects your input, the X, to be a two-dimensional table, like a column in a spreadsheet. Why? Because it's built to handle multiple inputs, like temperature and humidity. So even with just one feature, it wants it structured that way. If you get a shape error, just remember the .reshape command. It's your best friend. So our model is awesome, but it's not a magic bullet for every problem. It has one really big limitation, and it's actually hiding in plain sight, right there in the name. It's crucial to know when not to use it. See, it's called linear regression, and that's because it can only ever learn straight line patterns. But what if the real world is more complicated? Imagine it gets so hot that people stop going outside. Sales would actually go down. That's a curve, not a line. Our simple model would get that totally wrong. For that kind of problem, you'd need to reach for more advanced, non-linear models. So look at what we did. We took Jeff's simple logbook and turned it into a legitimate forecasting tool. But this is just the first step. Think about it. What if he started tracking other things? Is it a weekend, a holiday? How much foot traffic is there? Each one of those is a new piece of information, a new feature that could make his predictions even sharper. And that's the real journey of data science. It almost always starts with a simple question and a single straight line.
Like and subscribe for SimplfyTech, explaining one concept at a time, simplifying the technology and AI.